Welcome everyone to this third lecture of Mihai Putinar on moments in the context of Poema network. So this is the last talk of this series of talks. As before, questions are expected on the chat, and there will be some time for reading the question and maybe answering the question. So, Mihai.
Thank you very much. Hello, everyone. Today, I continue with some recent advances in multivariate moment problems, and in particular, an approach which probably is not well known but very powerful, done by two prominent complex analysts in Russia, Gennady Henkin and Shananin. But first, I would like to review a little what we did so far and what is the heart of Stiltius theory. So what Stiltius did, for different reasons, was to start with formal series. In the end will be the generating series of the moment sequence, and transform it into a continued fraction. This is a purely algebraic operation, which involves only divisions and multiplications and inversions in the ring of Lorentz series. And if that's the observation of Stiltius, if in this process all the parameters A in the continued fraction are non-negative, then when we stop at level k, this convergent, as it is called, is a rational function, has a very specific form. So it's a sum of simple fractions with non-negative parameters. That's the weight, that's, if you want, the pole. And the odd, that was the deep analytic observation of Stiltius, the odd, respectively even convergence always converge. Sorry for the repetition. They are called convergence, and we speak about their convergence. So it's nothing wrong with this. If these parameters in the continued fraction form convergent series, then the limits are different. If they are divergent, and these are many examples, then the limits are the same, and in the end we have the representing measure. So now at the level of measures, if we go a little back and see here, we take the point masses at this M and the weights. We consider this measure corresponding to the finite truncation. And what Stiltius proved is in the limit, we get an integral, an extended Riemann integral, what is called now a Stiltius integral, of this Cauchy kernel on 0 infinity. And to return to the data, this represents precisely asymptotically, not equally, the generating series we started with. So essentially, this is a very beautiful and complete solution of the moment problem, because we start with the moments, we put them in a series, we do purely algebraic operations, and a single test of the coefficients of this continued fraction will tell us that we have always a limit and the representation as Stiltius integral. So everything is well understood today, and it's remarkable that this is effective. So we can compute successively the coefficients of the continued fraction, and we have the point masses, so the sequence of finite atomic measures, which will converge to the solution. If there is no solution, then we have convergence to different measures, and any linear combination of them will be good. So also we have something very valuable, a continuum of solutions in the indeterminate case. Now, what is remarkable in all this, and I want you to remain with a very clear image, the coefficients, as we know from Jacobi and Kronecker and Hankel and so on, the moments are constrained, as you know, by determinantal inequalities, so by many polynomial inequalities, infinitely many, while the elements of the continued fractions are totally free. So this operation of just developing the formal series into a continued fraction somehow liberates the inner variables hidden in the moments. And that's very useful when you do parametrization of solutions, truncated problems, and so on. Now, later on, I mentioned a little last time Karleman and the school of Hilbert. This can be done not with continued fractions, but with infinite matrices. This is also very well understood. I'll not go much into this detail, but I want to mention that we start with the moments. We construct these elements in the continued fraction. Now we can be on the full line or on the semi-axis. And with them, we have a symmetric Jacobi matrix. In general, the AIs are strictly positive. The Bs can be anything real numbers. And what corresponds to the convergence of the continued fraction is simply what is called the finite central truncation of this matrix. That means we cut at a certain level. We have a finite matrix. The characteristic polynomial of it will be precisely the denominator in the rational approximation, what we talked about. So this is also very well understood. There is an operator theory approach to it, and in essence here, this is the proto-spectral analysis of symmetric unbounded possibly operators. And it entered into this field from vibration of strings, from Sturm-Liouville problems, from studies of touching equations of mathematical physics. Now, we like to go to several variables, and of course there are difficulties, as you know, and I like to show you how we can circumvent some of them with known function theory tools. Suppose we want to approach the moments of a measure in, let's say, Euclidean space R to the n. And as you saw already, it would be extremely useful to find a good choice analogues of similar transforms of Cauchy, Fourier, or Laplace. Now, what it is good in several variables, and this you have to be very much aware, is that if we have a big range of z's or x's and so on in these transforms, that means we know the function on a continuum, then we can recover the measure. There are inversion formulas. But what is more important, the moments of the measure, the power moments, are in general constrained again by inequalities, but even more so. We don't know exactly a characterization of moments of positive measures in Rn. But what we know for sure is a characterization of either one of these transforms. There is Borner theorem for Laplace. There is Wheeler Gilbert transform for this. There is Bernstein theorem, and I'll mention all this today for the Cauchy transform. So from the practical point of view, and I know that you are all interested in applications and to implement this in engineering or optimization, you name it, my advice is look first at classical transforms and then work with just discrete moments. So to do this, we have to go back a little and see what it is behind the one-dimensional setting. And you remember we have this correspondence between functions, resolvents of operators and measures. And this is the key, the starting point, very well stated in Ritz-Herlot's theorem. So with your permission, I'll go back to this and then try somehow naively to extend it to several variables. We start with an analytic function, complex analytic function in the unit disk, which has non-negative real part. And the theorem of Ries and Herlot says that always this function has an integral representation. Here is a purely imaginary constant and kind of Cauchy transform of a positive measure on the boundary. I call it a T, the torus. This goes back and forth. And there is a bijection between such functions and measures. This can be transformed by Cayley conformal mapping to the upper half plane and gives exactly the representation we encountered already in the previous lectures. So how do we prove this? Let me go quickly so that there is no mystery why this is so. We dilate a little the function, and there is no harm to consider after such a dilation that the function is defined in a boundary of the closed disk. Then plain Cochi theorem, here you can write the Cauchy representation formula and play a little with it. It's two lines. Will show that this dilation is almost what we want. The measure being now the real part of the function. Now this is defined on the torus, before it was not. Times this is simply arc length, normalized arc length, d theta. But we remark that if we consider these measures, positive measures, the total mass is always the same, is the value of f at 0. So they form a weak star compact family. We can pass to the limits and we have what we want. We can avoid here the weak star convergence, but it's the quick way to resolve it. Now, these functions form a convex cone, obviously. If I multiply such functions with a positive scalar, they say there. If I add them, they are there. And what is important here, for the moment problem, this is crucial, is to identify the extremal rays in this convex cone. And that's, again, very easy because we have any measure there. What would be, let's say, the extremal points in the set of measures with prescribed mass, probability measures? Obviously, point masses. They correspond to rational functions, exactly what we expect, and they generate everything. Now, I want to play the same game in several variables, and today I focus only on the unit ball. There are many choices here. The unit ball is important because it has a lot of holomorphic symmetries. And I would like naively to extend Ries-Herlot's theorem to the unit ball. I start with an analytic function. This makes perfect sense, positive real parts. And we can repeat exactly what we did before. The sigma is the area now is not arc length, but the surface area of the sphere. And we have a positive measure as a limit, exactly as we did before. And we have the representation. I put it in this form because it's more valuable. Why we have this denominator? Because this is the analog of Cochi's formula for the ball, the so-called Segue kernel. It's again a very simple computation, which, by the way, you can verify it on monomials if you want. So we have such a representation, we got a measure. What breaks down here and what is the whole complication is that not every measure can appear here, although here we have all functions with positive real part. So the proof, I'll go quickly. These are just the notations, the Hermitian inner product. The Cauchy Segue kernel is this one and has the property of reproducing an analytic function in the neighborhood of the ball. So here is the proof using this reproducing kernel. If I integrate on the sphere this analytic function f times s, with the reproducing kernel I get the value as z. I take the conjugate, so plain manipulations, and I have the polarized real parts, and what we have here also a polarized product of the kernel. By the way, remark that this is positive semi-definite if you know kernels and their property of being positive semi-definite, because this is positive. So altogether, we put this at work. We take limits as before and the space of measures, and we have what we want. That was relatively late observed by Korani-Pukansky, and independently Eisenberg, Dautov, and the whole Russian school. And they remarked that this measure, which represents an analytic function with positive real part, is not arbitrary. There are such unpleasant moment conditions. Such a measure annihilates all mixed moments when the powers, multi-indices, are not comparable. And also there are these vanishing conditions, if and only if. And there is a reason why it is so. I'll not enter into this detail, but already we see that there is something interesting now characterize these measures. Can we somehow put our hands on these measures? And unfortunately, we cannot. So positive measure, let's say we call it a P measure if the analog of the Poisson transform, I'll use some technicalities here, is pluriharmonic. That means the real part of an analytic, complex analytic function. And then in this case, it is exactly as we computed before, the boundary limit of the real parts against area measure. There are, by the way, I see a question. You will have, Alejandro, very soon quite a few examples of measures which are not there. And I'll give references. So it's coming. Or we can use just a standard Poisson kernel. And obviously, we consider in our approach only positive measures on the sphere like this. Now, they were studied quite well. And for instance, Forelli, an associate of Rudin, had a lot of interesting remarks. For instance, showed that such a measure has a diffusion, is spread everywhere on the sphere, cannot be concentrated on a variety of real dimension 2n-2. So if this is a Borel set and this set is thin, even when we circle it, we multiply with the full torus, the measure will not charge this with any mass. So Alejandro, no point masses, no integration against low dimensional varieties. And moreover, if we have the invariant measure, we pass to the projective space here, the quotient of the sphere, the absolute continuous part of this measure, if you want, or the proportion of this will be exactly the invariant measure on the projective space. So this is almost like an area measure. Now, Alexandrov has a deep understanding of these measures, and for instance, he shows that if we take a Euclidean ball on the sphere, this measure puts charge on the ball comparable to these respective powers of the radius. So it's really heavy on balls. So corollary, if such a measure is non-zero, then the support is the full sphere. And the bounds here, you can see immediately, are optimal for the rational function and so on. So let's go back a little and see what we achieved. If we take all analytic functions positive real part, normalized at 0, they can be written in this form now with a function which takes the ball to the disk. That's just Cayley transform. And so this is 1-to-1. The real part is what is called pluriharmonic. And we have the representation with this P measure. Now, big open problem. Since the 60s, nobody has a characterization of the extremal P measures. Obviously, they form a convex cone. We have quite a few examples and criteria of extremality, but there is still open and would be, for moment problems on the ball, extremely useful, illuminating, to have a description of all extremal rays. So there are some conditions I put at the end of the tutorial. I'll not go. Hello, Bernard. We'll see in a minute what we get if we take any measure. So just bear with me. We go exactly, you anticipate, in that direction. We have criteria. Forelli has one. I'll not go into this detail. It has to do with factorization of these functions. And the 1D application is very simple. I let you go over this because I want to touch, I have 20 minutes or more, some more constructive aspects here. So the idea, there are several ideas here, and in practice would be very useful to disintegrate these measures. So to take slices along arrays, like in tomography, for instance, and then we have a one-dimensional measure and a probability measure we know very well, and the representation. Fortunately, this disintegration is very useful, and we have a continuous map from the projective space to the probability measures, and we can go even deeper into this this structure. This was done by Alexandrov. Just to tell you that the naive way of disintegration along arrays passing through the origin is useful here. Now, on the one-dimensional case, we saw that this is the key transform. And second characterization of these measures, this is a work I did with Farhad Jafari, a student of Rudin, gives again rather useful for applications characterization of the slices. Namely, we take the Cauchy transforms of this projections on rays, and the two conditions here characterize the P measures. So we have, if you want an integrability condition here, we can put together all this this family of automorphic transforms into a single measure. And at the level of moments, of course, the disintegration works as you expect. So you essentially split the variable into an element on the unit sphere and a positive scalar. You fix zeta and you let lambda free. And then you have a moment problem in one variable. And then the whole principle here is to put together these moment problems along arrays. Something, again, which is done in tomography quite often. Now, if we want to, as Bernard asked, to produce a lot of analytic functions with positive real parts, we do not use the Cauchy kernel, the Cauchy-Segur kernel, but rather we mimic the standard Cauchy kernel in 1D, now in several variables. And this is very useful. It's called the Fantapie transform. It's very well studied in duality theory. I'll mention briefly. And what is important is that this is related to the Laplace transform. So just have a quick look. I want to produce this denominator. So I take the, let's say, Laplace Fourier transform of the measure, supposing that this decays fast enough, with a parameter t here. So ZW bar is just the inner product, t. I take, so that's Fourier transform. I take the Laplace transform of this, and if the measure decays fast enough, where we are on the sphere, for instance, then I can switch the order of integration. And the integral of the exponential between 0 and infinity produces precisely this, this denominator. So here we are hand in hand between Fantapie and Laplace transforms. And this is extremely useful, as you will see. Now, why Fantapié transform is good? Because it gives you duality between the space of analytic functions in a convex domain, say, and germs of analytic functions in the dual. Now, the dual is with respect to this polarization, this form. So I take all Z, this is in Cn, sorry, not C, so that the inner product is not 1. And I take the component of infinity, connected component of infinity there. And this was observed by Martineau, and then there are several proofs. One, I'll give you references, which is related to what we are doing, goes through Hilbert space and is sketched here. So what is important is that this transform takes an analytic function. So if this measure is analytic function times, let's say, the area measure, inside to an analytic function on this polar domain. Obviously, if the denominator doesn't vanish, this is analytic in Z. And the duality is well understood, like in the 1D case. By the way, this was done by Grothendieck a long time ago, and gives us what Martineau Heisenberg stated. I'll not go into these details. It's a question of taking limits, direct inverse limits, but it's very straightforward and very useful. Now, the inner product we are interested in, here should be a B also, my mistake, is not the standard inner product, let's say like in the Hardy space, but we have this combinatorial coefficient in front. So again, the monomials are orthogonal, but with precisely this factor. This comes from the denominator we use in the Fantapié transform. And there is a positive definite quadratic form here, defined on monomials or on a convergent series, which goes exactly like this. Why do we carry these two, like in Fourier transforms? It's a question of the constants, how we count them. And now for our purposes, it's very useful what we did, because if we take all analytic functions with positive real part, let's denote it by O plus, and we take all transforms, Fantapié transforms of them, normalized as in Ries-Herlotz, we get such a representation. The key point here, and this I think explains what Bernard wanted to see, is that the kernel here has positive real part on the ball. We cannot work with a Segur kernel because we'll mess up everything, and if we take a positive measure, will not be positive real part. But this kernel is good, as you can compute immediately. So in this representation, all positive measures are allowed. Of course, some of them can have the same output here. But it's still good that we free this condition of Korani-Pukansky, and we allow all positive measures. And what I proved with John McCarthy about 10 years ago is that in our standard duality given by the kernel, the two classes are dual to each other. So we cannot find exactly the extreme points of this convex cone, but at least we have a good description, and here we allow all measures of its dual. And this is useful. if we look just at examples, extremal situations will be quite useful. And you can see this integration here at work. I'll let you read, if you are curious, these slides, because I'm looking at the watch and want to arrive somewhere else. And you have, therefore, a completeness and an approximation even. But here we encounter the same difficulties as in the standard construction of Kubarchuk formulas in several variables. How to find these weights and points. There is no royal way, as in the Stiltes case, where you take pure algebraic operations on the generating series and you have everything. Here it's a little more involved. And the approximation and so on, I'll not go into this. Now, non-uniqueness, that's important. If we take a big circle, we saw that this is not a P measure. And we integrate along the big circle, the kernel, we get always 1. So this shows that there is a big ambiguity, a big loss when taking the Fantapié transform of any measure. There is a non-uniqueness here. I skip this. And there is a Padea rigidity. Now, where I want to arrive, and this is the observation of Gennady Henkin, based on much earlier works of Sergei Bernstein. We take the Fantapié transform. I put a parameter here to make it homogeneous, and I denote it by phi. And I remark that this has a positive imaginary part. It depends if you took a plus or minus here. And this, of course, reminds us what we did last time in 1D, the Markov transform. So we have an analog of the Markov exponential transform. Take the Fantapié transform of a measure on a convex cone here. It can be written with what we call a phase function along, again, slides here. And for this phase, the moments, if the moments of this exist, the moments also exist. And they carry all information. Now, why this is important? A measure can be very wild, you know. It can be singular, and it's much more easier to deal here with integrable functions, even if they depend on a parameter, than with measures. And I use this specifically for the entropy method in the moment problem, and I'll give you some references. So what is important in this observation when we work with convex cones, that we have an extension of the Fantapié transform on what is called the tube domain. That means we put a condition only on the real part of the parameter u is in the interior of the cone. This is the dual. And the real part of u naught to be strictly positive. And then everything doesn't vanish here. We produce an analytic function in u naught and u, homogeneous of degree -1, which is surprisingly fully characterized by a set of simple conditions. So it's defined on a tube domain and can be completely characterized. So that's good news. We start with an arbitrary measure here, and we can analyze it with complex analytic tools. Now, why the tube domain? Maybe you know, these are the analogs of the upper half plane, and they carry a rich group of holomorphic transformations. So they are homogeneous domains, and you have a full harmonic analysis related to them. And this plays a role in the analysis of this, in the decomposition and all properties of such transforms. So that's a little the discussion of the tube domain and harmonic analysis there. I go a little fast. And then we have an immediate characterization exactly a la Ries-Herlotz. So first, the classical result for Laplace transforms, but also for Van-Tapier transform. This you have to know is old. Sergei Bechstein had it in one variable, extended by Bochner to several variables and Gilbert. As I said at the beginning, the moments of a measure are very mysterious. These transforms are less so. So we take the Laplace transform of such a rapidly decreasing measure at infinity on the dual cone. And this, if we take partial derivatives, will satisfy a sequence of inequalities. But what is remarkable, and that was observed by Bechstein, that this is if and only if. So these functions are completely monotonic, these conditions on the derivatives on the respective domain on omega. And they also characterize the Van-Tapier transforms of positive measures. So here we are on solid ground. We start with any measure. We lose nothing. By the way, this can be inverted, as you know. And we have characterization of the transform. For the Van-Tapier transform is Henkin-Shananin. This function has such a representation on the dual cone if and only if is homogeneous of degree -1, obviously, and completely monotonic in the previous sense in the interior of the dual cone. If and only if. And again, I repeat here, there is no characterization of moments of such positive measures on a convex cone. Now, what is useful here, as I mentioned, is the harmonic analysis on the tube, the analog of the Hardy space, if you know. If not, just skip this part. There is an analog of the reproducing kernel, a very simple formula here, which has the reproducing property. So the analog of the Segre kernel on the Hardy space on any tube domain, which now we repeat the proof of Ries-Herlotz. We did it before. And we get exactly a kernel, which I call the Herlotz kernel in several variables attached to any convex omega, which has exactly this form and gives the representation of the function. This is constant in terms of it and the real part. So it's exactly Ries-Herlotz. It goes back and forth. And here is the theorem. If we put together everything, start with a measure on the convex cone, take the Markov transform. This Markov transform in its turn will be the Herlotz transform of a function which has values between 0 and pi. There is, of course, a normalization here. We can make it 0 and 1. So what is remarkable here is that we can distill the moments and all the information of a very nasty measure into a function which is much more prone to approximation, let's say, with Fourier methods, with orthogonal polynomials, and so on. And again, the vanishing moments can be understood, the analog of Korani-Pukansky and Eisenberg-Dautov, they are here for this function, so not every function. And there are quite a few examples. I'll give you details. I'll finish very soon. So you can do this on the positive octants, explicit examples, and you will see that we obtain precisely the transform we encounter in one variable on the upper half plane. This is simply the kernel which we used in the 1D theory, which appears essentially in Stieltjes and Hamburg. Now, references. And then I'll be open to discussions very soon. Alexandrov in the Soviet Encyclopedia has a very beautiful article, long, you see, 80 pages, about the function theory in the ball, and you can find a lot of important information about these P measures on the ball there. The 1D case is classical. I mentioned last time also this paper of Aronjain and Donoghue, still of much interest when you want to do the Markov transform. My work with Marko Budisic on where you can find all the details on this last result and its potential importance for the entropy optimization. If you want to see the harmonic analysis on tube domains, there is this beautiful book by Farrow and Korani, again Korani. Now, the less known application of these tools to optimization, in fact, to mathematical economics is in a series of papers by Gennady Hengin and Shanani. I put only one here, but you can dig out more, and you can send me an email if you don't find them. I have them in a PDF copy. The duality, what I worked with John McCarthy is in this paper, and I have to mention 2D analog and, if you want, framework, a parallel theory, which I developed over many years and is in these lecture notes with Gustafsson, also based on an exponential a la Markov transformation. So this is specifically 2D. What I didn't touch here, this will be for future encounters, hopefully we'll have the opportunity, is the operator theory approach, which goes into understanding deeply these kernels which appeared in our computations. Many people contributed and continue to work here. A big name here is Jim Arler, and then a lot of associates and students. And also very I would say obscure, and unfortunately so, is the theory of branch continued fractions. You may ask, okay, we started with continued fractions, what can we do in several variables? Quite a lot. Very messy, but very promising. There is a whole group of mathematicians, I think Skorobohatko was the father of them, and then Bodnar and a few others in Ivano-Frankivsk. This is a city northeast of the Carpathian Mountains in Ukraine. They developed this, and there are books, there are articles. Use your, if you want, curiosity just to touch and see how continued fractions appear in several variables. And also, more recently, they made a breakthrough in combinatorics due to the work of Sokal and collaborators. So these are two directions, two ramifications linked to what I mentioned, but not touched in my lecture. And I put here a tutorial if you want to warm up a little and see what Forelli did is here, just a few lines to understand what is at stake. And to finish, maybe I should mention big open problems. So in several variables, the characterization of moments of positive measures unknown. Necessary conditions for uniqueness in the several variable setting unknown. We have sufficient conditions, quite a few. Some of them are classical, some of them are in the book of Konrad Schmidgen, some of them are in just research articles. And I would say, related to what I talked today, a characterization of extreme points in this set of analytic functions with positive real part. There is some progress here due to Greg Gnesi and Michael Jury. I let you dig out the details. You have to accept some terminology, some facts of operator theory, but still there is no solution to this problem. So I stop here, and I'm happy to see questions.
Thank you very much for your nice presentation. Yes, so if there are questions, they can be in the chat. Maybe also turn your microphone if you want.
Sure. You can send me later emails if you have questions.
A question which maybe is easier to say than to write. So in the truncated case, so when we have a finite set of moments or discrete information, are there some results which are known using this different transformation?
Sure. So everything which I mentioned here transfers to the. So in particular, you mean this transform? Yes, it will not be equal, but you can do it formally. You can take the formal series here, and you will match the moments, and you will have then there is a bijection between the truncated moment problem for this, let's say, nasty measure mu, and the truncated moment problem of the nice phase function phi. So that's for sure. Obviously, for Laplace transforms, there are results of this sort. I don't know offhand, but probably if you cut here, with a degree and you put a monotonicity condition, there are obviously studies when this can be extended to a completely monotone function. So germs of such Taylor germs of such functions. I don't have the reference here, but obviously this exists. But nothing as nice as complete algebraic manipulation, which gives you the rational approximant and so on. I don't expect something like this to happen. Very simple reason. Let me go back to the beginning of this story. So suppose we are in several variables. We'll have not one, but corresponding to multiplication by the variable, several Jacobi matrices, Jacobi type matrices. They commute when they are infinite. If we cut them, they stop commuting. And that's the main difficulty. That if you do a finite center truncation uniformly on, let's say, a pair of commuting self-adjoint operators, they will stop commuting. And then you can still do something, work with non-commutative variables and do a non-commutative calculus. And this is quite successful in this approach I mentioned at the very end in two variables, what I call the hyponormal quantization. In two variables, this works well.
Thank you. Do we have other questions?
All right. If not, please send me emails anytime. I'll be happy to correspond. And it was a pleasure. I hope I gave you some information which on purpose is not easily available. So I have chosen complementary subjects which you don't find easily in books. And I wish you success. And
thank you very much for your 3 lectures. And also, I want to thank you all the participants for following these courses. And this is an end of our series. Goodbye.
Goodbye. Be well all. Stay safe and be prudent.